A heavy-duty transport truck is operating at highway speeds of 85 kilometers per hour. The front axle tire, a standard 315 by 80 R22.5, is carrying a near maximum structural load of roughly 4,000 kilograms. Without warning, the sidewall casing suffers a sudden, explosive rupture. Internal pressure violently tears through the reinforced rubber and steel layers. Statistically, 90% of catastrophic highway tire blowouts are unrelated to punctures, potholes, or external impacts. Accident investigators frequently look at shredded casing on the side of a highway and assume the vehicle struck a piece of sharp road debris, misattributing the failure to bad luck rather than complex internal physics. Because the vast majority of these blowouts lack an external mechanical trigger, failure analysts must quantify the specific internal heat generation and material fatigue leading up to the rupture. In the forensic lab, the ruined casing shows no evidence of general wear, as the tread remains partially intact. The exterior inspection yields two severe anomalies: a massive 150-millimeter crack along the sidewall and distinct visual evidence of localized rubber melting and glazing around the rupture site. Crucially, an exhaustive inspection of the rubber surface reveals zero evidence of a puncture object, cut, or external penetration. The casing was breached from the inside out. Moving the investigation to the internal structural components, the exposed steel cords near the belt shoulder exhibit a distinct unnatural bluish discoloration. Metallurgical discoloration of this specific type occurs exclusively when internal operating temperatures breach 120 degrees Celsius. The physical evidence points directly to an extreme internal thermal event. This proves we are looking at a classic thermal fatigue failure, leaving us to reverse engineer exactly where that extreme heat came from. To find the heat source, we have to rewind the timeline away from the final explosion, back to the initial steady-state operating conditions of the tire. This 2D cross-section illustrates the mechanical origin point. Due to a slow leak or poor maintenance, the internal pressure drops from a normal 8.5 bar down to 6.5 bar. This 20% drop in pressure creates an immediate geometric consequence. At 6.5 bar, the tire can no longer maintain its designed profile, and the contact patch surface area increases. Pushing a massive 4,000 kilogram load onto this widened footprint forces the newly underinflated sidewalls to undergo extreme physical flexing with every single rotation. Structural stress is inversely proportional to internal pressure. By dividing the constant heavy load by the reduced pressure, we see a 30% concentration of structural stress heavily localized right in the bulging sidewalls. This concentrated stress deforms the load-bearing polymer matrix far beyond its design limits. Underinflation creates a severe geometric distortion that initiates an exponential internal stress cascade. That mechanical flexing directly translates into thermal energy through a thermodynamic concept known as hysteresis, the process where viscoelastic polymers generate internal heat when subjected to continuous cyclical compression and release. This rolling tire cross-section maps out the mathematical reality of that flexing. We have a heavy vertical load of 39,240 newtons, an elevated rolling resistance coefficient of 0.008 caused by the underinflation, and a velocity of 23.6 meters per second. We can calculate the baseline rolling resistance force by multiplying the load by the resistance coefficient, which gives us 314 newtons of continuous drag. To find the total power generation, we multiply that 314 Newton force by the 85 km per hour highway velocity. The resulting calculation is staggering. The compromised tire system is actively generating approximately 7,400 watts of thermal energy directly into the shoulder. A heavy-duty truck tire is thick and insulated. It lacks the surface area and airflow required to effectively dissipate this volume of trapped heat into the ambient air. At highway speeds, the underinflated tire ceases to function as a stable load-bearing structure. It transforms into a runaway 7.4 kilowatt thermal generator. We can track the microscopic impact of that trapped thermal energy by looking closely at the critical boundary layer between the internal steel belts and the surrounding rubber matrix. This line graph demonstrates the exponential decay of the tire's structural lifespan. These polymers follow a strict empirical rule. Every 10 degrees Celsius increase in internal temperature cuts the operational lifespan in half. Pushing the nominal 80-degree operating temperature up to 110 degrees immediately drops the remaining lifespan to just 25%. Crossing the 120 degrees Celsius threshold initiates rapid chemical softening. The intense heat permanently breaks down the chemical adhesion strength, decoupling the steel belts from the rubber bond. This animated microscopic view displays the Paris law equation, which governs fatigue crack growth. Continuous cyclic shear strain at 85 kilometers per hour begins to exploit this thermally weakened adhesion zone, initiating a tiny microcrack. With every single rotation of the wheel under that 4,000 kilogram load, the microscopic void physically tears wider and deeper. High-speed cyclic rotation combined with severe thermal softening guarantees that this microscopic void will inevitably propagate into a macroscopic structural failure. This flowchart tracks the uninterrupted sequence. Underinflation triggers severe hysteresis and heat buildup, leading directly to polymer softening, belt separation, and a catastrophic burst. The terminal phase begins the moment the microscopic crack reaches macroscopic size, completely severing the steel belt from the casing edge. The 6.5 bar of highly pressurized internal air instantly floods into this newly formed structural void. The chemically degraded, melted sidewall has no capacity to contain this sudden internal pressure spike. The casing violently tears apart, resulting in the explosive rupture. The catastrophic blowout is the terminal outcome of a predictable, unmanaged thermodynamic loop. Preventing these thermal fatigue failures requires breaking this thermodynamic loop through targeted engineering interventions across structural, material, and system-level domains. This 3D cutaway highlights a primary structural improvement, a nylon cap ply wrapped tightly over the steel belts to constrain outward shear growth. Additionally, low hystereses, heat-resistant rubber compounds are engineered to reduce friction and maintain chemical adhesion past 120 degrees Celsius. The most effective solution operates at the system level. Real-time active monitoring, like a tire pressure monitoring system, directly targets the root cause, alerting the operator the moment internal pressure deviates from baseline. Paired with integrated load sensors, these dynamic readings ensure the vehicle avoids excessive sidewall flexing, preventing the initial structural geometry distortion from ever occurring. A heavy-duty tire never suddenly fails. It slowly degrades along a mathematically predictable continuum, until the structure can no longer contain its own internal thermodynamics,